Reservations in two-way slabs by means of yield lines. This video will deal with cases 26 to 30. It means it's about slabs which are on the longest side fixed, on opposite sides fixed, and on the shorter side they are simply supported. And we will deal now with case 28, which gives you an edge square reservation on the top side of the slab. Reservations in two-way slabs, case 28. We first take a look at different geometric characteristics of case 27. The longest side B of the slab must be between A and 2A to have a two-way slab. The reservation is square, so D1 is equal to D2, and it's at the top edge, so it means that D3 is 0, and it must be between the two yield lines, so from left to right. So it means that, of course, D4 must be bigger than this point here, which is the slope. It's 1 over S4 times D1. And on the other side, this is the distance B minus again this slope, then minus D1. We can substitute the values of the S parameter, and we arrive at those conditions. We see that D4, the condition on D4 depends also on the size of the slab. We can now visualize the different possibilities, which is quite straightforward. It's a rectangular reservation going from, for instance, left to right without crossing the yield lines. These are the parameters of the slab, and the work or the work done by the external forces is now equal to, when we take the blue elements, then we see that it's composed of triangles. So we have A times S1 and A times S3, and the mean deflection is delta over 3. And then we come to the rectangular portion, which is this side, which is B minus S1 minus S3 times A. But now we have the reservation in it, so we subtract the reservation, which is D1 times D1, and the maximum deflection there is, of course, D1 divided by S4. And we take the mean deflection, so it means that multiply everything by delta over 2. We substitute different parameters, and we got this equation. The work done by the internal forces. First, we take the negative yield line, which is B minus, of course, where the reservation is, minus D1, and the angle of rotation is D1. The angle of rotation is delta divided by 4. So we got B minus D1 divided by S4. This yield line projected on this axis of rotation, it's B divided by S4. And here we have B divided by S2. This yield line is also B divided by S2. And on the other side, we have A divided by S3, and we got A divided by S1. Then we substitute the variables, and we got this nice expression. By making D equal to E, we can get M, the bending moment, and the bending moment is a function of alpha and alpha 1, and this is the expression. First thing we notice is that this expression is independent of D4. So D4 drops out of the equation. But must be careful, because the conditions for D4 must be fulfilled, even if it's not in the equation. We give an example of a slab with a rectangular reservation in it of 1.5 by 1.5 at a distance of 1.75 meter. The concrete slab is 200 millimeters with a concrete cover of 40. Floor finish is 2 kilonewton per square meter and a mobile load 20. Now, what is the needed reinforcement? First, we calculate the load in ultimate limit state, which is 1.35 times the permanent load plus 20 times the plus 1.5 times the mobile load, and it gives you 39.45 kilonewton per square meter. The different parameters, and then we can easily calculate the maximum bending moment as a function of alpha and alpha 1, and we get 26 kilonewton meter per meter. We convert this into reinforcement. First, we calculate the lever arm. The mean lever arm is then 152 millimeters, and the needed reinforcement is 110 times the maximum bending moment divided by the lever arm and the yield strength of the reinforcement, which is 480 square millimeters per meter. Or it can be done by diameter 8, 10 diameters 8 per meter. So it is in X direction, Y direction, top and bottom, so 4 times. If you want to calculate it a little bit more economically, then it's 8 times diameter 8 every 105 millimeters. But this is preferred. It's easier to handle. Or you can choose for a diameter 10 because the slab is 200 in depth. So if this is too much, we can take a diameter 10, we fill in there the diameter 10, you will have a different lever arm, 150, recalculate the reinforcement, and then diameter 10 every 160 millimeters is also fine. Second example of an existing slab, reinforced in both directions, top and bottom reinforcement are equal. We do not know the amount of reinforcement nor the original load where the concrete slab was calculated for. Now we wonder, is it possible to make a rough reservation in it for a ventilation shaft of 2 by 2 meters? The parameter alpha is B over A, so this is 2, and alpha 1 is 2 divided by 5 gives you 0.4. So the maximum bending moment can now be calculated without the hole, which is M0 divided by the load. This gives you a portion of the equation which is independent, it's only dependent on geometric characteristics, and we have 0.985 meters per meter. We can calculate the maximum bending moment with the reservation in it, and we got 0.949 meters per meter. So this means that the bearing capacity is 104%, or it means that this type of reservation does not touch the existing bearing capacity of the slab. So now you can decide they can make this reservation in the slab, even if you do not know the original capacity of the slab. The bearing capacity is defined at 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. In formulation, something like that. We work with dimensionless parameter. And for case 28 types of reservations, we have the restrictions, of course, of the two-way slab and the position of the reservation. We will show you now how to use this condition, because in the previous example, we did not use this condition. This is the condition with the parameters D4 and D1, but you can also work with unitless parameters. Then the bearing capacity using this formula and the formulas of the previous slides, you arrive at that in this expression. You can put this in a graph for different values of alpha going from 1 to 2. And on the x-axis, it's alpha 1 going from 0 to 0.5 times A. And these are the different values of the bearing capacity on the y-axis. You notice that almost for this type of case 28 reservations, you have no loss in bearing capacity, unless in the beginning for small reservations, you can have small loss in bearing capacity. The when you have alpha between 1 and 2, then you see that you start having loss in bearing capacity from the size of the hole equal or smaller to 0.263 times A. From that moment onwards, you will have a small loss in bearing capacity. So the smaller the reservation, the bigger your loss in bearing capacity. Now, how will you use this condition? Alpha 4 must be between those two limits. So if those two limits are equal, then it's still fine. That's the limit. So that means that alpha 1 must be smaller than 0.46 times alpha. So when there is a value of alpha bigger than 1.08, then alpha 1 is between 0 and 0.5. Because you have two conditions of alpha 1. That's the first condition, and this is the second condition, in fact. Because alpha 1 must be chosen in such a way that alpha 4 is possible. So this is the limit. And for alpha smaller than 1.8, then alpha 1 must be between 0 and 0.464. So this means that, for instance, for the red curve, alpha is 1, then you see, because alpha is smaller than 1.08, that alpha 1 is now limited to 0.464, otherwise this cannot be fulfilled. Otherwise this will be to the left. So it means that this red curve is not valid in this portion where alpha 1 is bigger than 0.46. So we look at the graph of the previous slides. We have seen this region. You can now, on a bigger scale, we can look at it, and then you see that from those values, from reservations bigger than 0.28 times A, there is no loss in bearing capacity. Smaller reservations give you a loss in bearing capacity, but this is not significant at all. It's less than 1%. So you can have a general conclusion, which is that there is no bearing loss when the reservation is larger than 1/4 of the smallest size of the slab. But in this case, the loss in bearing capacity is not significant. So square hole at the edge of a rectangular concrete slab type 28 has no significant loss of bearing capacity as long as the yield lines are not crossed. And these are the different types that you can have from reservations.